Okay, beginning part 2 here. I've decided to divide the video into at least 2 parts. This may not be the last one, but I'll call it part 2 for now. And what I would like to do is test the tubes. I've gotten out a B&K 707 tube tester. There are lots of tube testers, and I've done a bunch of videos on them, so I won't belabor the point here, but basically understand that while there are better tube testers and not so good tube testers, there's no perfect tube tester. They just give you an idea of whether the tube is good or not. They don't necessarily tell you that it'll work in a particular circuit. So the way this particular tester works is you find the proper socket. Now, for some, that's easy because it's listed right alongside here. For other tubes, you look it up in a book like this. But at any rate, you wind up testing either using this top panel or this bottom panel, and you switch between them with this switch over here. Like I say, I'm not going to give you a tutorial on using a 707 tube tester, but we're using this upper panel, and that's where we have this tube plugged in. It's a 5Y3. And so now we're going to give it a shorts test. We push the shorts button, and we see nothing on the meter, so there are no shorts. Then we test number 1, which is one side of the 5Y3, and you see it's very good reading. Then we do test number 2, and that actually goes off the scale. Let me see if well, it's about 30. So that, anyway, that's a very good. Now, I've had this warming up for a very long time, so it doesn't surprise me. Besides, this is a rectifier. And understand, when you're testing a rectifier, it doesn't matter whether you're using an emission tube tester or a dynamic conductance or mutual conductance tester. This is a mutual conductance tester, at least the upper panel is. The lower panel is for testing tubes that aren't wired up for the upper panel, but it does not test for dynamic conductance. It only tests for emission. So the cheaper tube testers are like this one down here. The more expensive are like these up here. And for certain tubes, the difference is important, but for this 5Y3 it's not. But at any rate, it's a good tube. So I'm going to continue doing the tube tests, and then I'm going to move on to doing tests of the voltages in the SX71. Before I get to the voltages, though, I do want to make a short statement about safety. Number 1, while this particular receiver has its own built-in isolation transformer, in general, you should always use an isolation transformer, even if it has a built-in isolation transformer, until you have verified that you do not have a hot chassis. Because once you take this out of its case, if you touch this chassis and it's hot, it can kill you. So be very careful. Make sure you do not have a hot chassis. If you don't know what that means, if you don't know how to test for that, I suggest you don't work on any of these receivers. When I first started, I had a mentor that was standing beside me the whole time until I had completed many, many hours of practical training under his watchful eye. And only then did he trust me to work on these kinds of sets. And even then, he made sure that he was in the shop. He might not have been looking over my shoulder quite as much, but he was not far away. I suggest if you have not had that kind of training, don't work on these sets. They can kill you. So with that, I'm going to move on and finish testing these tubes. I thought I might show you one of these. This is a 6BA6 that I'm testing. It goes up here in socket number 1. It's a 6-volt filament. And this is a tube that is being tested for mutual conductance because it is an amplifier tube. But the reason I wanted to show you is, if you will notice when we press test 1, and this particular tube only has one section, so we only have one test, it barely gets into the good, and then you notice it starts to fall off. That is an indication of a tube that is losing emission. In other words, what happens is, while the tube is sitting there and the heater is hot and the cathode is hot and the cathode is emitting electrons, but it's not drawing any current, it gathers a lot of electrons around the cathode. It forms what some people call a virtual cathode. In other words, a collection of electrons right near the cathode, ready to sweep up to the plate. When you first press the test button, or when you first apply a signal to a tube like this, it has enough electrons to perform in a somewhat normal fashion. But then, as those electrons get used up and the cathode begins to dissipate its spare electrons, its emission falls off. So watch again what happens to the meter. In the green, and then starts to fall. Now this is a fairly subtle phenomenon, and frankly this tube might very well work in this receiver. But I'm going to mark it as questionable because it looks like that if it isn't bad now, it probably will be in the near future. Now there's yet another way to do the same thing, and that is to use the life test, which is this switch. I'm going to push it over, and then I'm going to push test 1, and watch what happens now. You see, it moves down even into the replace region. So this is a weak tube. It's working, but barely. I have finished testing the tubes. There were 3 of them that tested a little weak or questionable, but I'm going to go with them for now. And the next step is to test the voltages in this SX71. Before I get to that step, since it involves powering this unit up with the covers removed, remember that if you're not trained on this kind of equipment, and by trained I mean if you haven't been through either an industrial or a vocational training program in electronics, or you haven't ever worked with a mentor, an experienced person like a ham radio operator or a former technician or even a present technician or teacher who understands this. If you haven't gone through something like that, don't work on these. And when I say training, I don't mean watching a YouTube video. YouTube videos are great, you can learn a lot, but the one thing you do not want to do is work on equipment like this, especially by yourself, without a lot of training and someone looking over your shoulder who knows how to keep you out of trouble. So that's my first safety lecture. I'm sorry to keep repeating it, but it's really important. The second one is, you'll notice over there is a variac that I'm going to be using. And if you haven't watched my video on the depth difference, understand that a variac like that is not an isolation transformer. Fortunately, this particular receiver has an isolation transformer built in. But you should always use an isolation transformer, even if you have one built in, until you have verified that the isolation transformer that's built in is working correctly. And what I mean by that is, you need to actually test to see if you have any line voltage leaking to the chassis or any metal parts where you can make contact with it. If you don't know what I mean by that, then best to just avoid this altogether, or at least use an isolation transformer in addition. Okay, well, enough safety lecture. I know it bores those of you who already know this, but you're also the ones who know how important it is. So let's move on to doing the voltage readings in this receiver. Now, what you see here is a chart of voltages that comes from the service literature. And as I pointed out earlier, you can download this manual from the Boat Anchor Manual Archive, BAMA manuals. This shows a bottom view of the chassis, and each of the tubes is one of these circles. For example, this is V7, and then the voltages around it. Now, in the SAMS, that's the writer. In the SAMS literature, they have instead a chart like this. It's the same information. The voltages vary a slight amount, 5% here and there, because of the different conditions, and we'll talk about those in just a second. The whole point, though, is that you need something to reference against. Now, what I have also done is prepared a little thing using a spreadsheet program to allow me to write down the important voltages. I probably won't write all of them down. Basically, what I'm interested in are the grid and plate values, and perhaps the cathode values in some cases. So let me move on to that, but before I do, point out that one of the important things is to always read these instructions to see what were the conditions under which the voltages were measured. By conditions, that means a number of things. First, how are all the controls on the front of the unit set? Second, what was the line voltage? And third, what was the meter that was used? Now, we are going to use a multimeter, a digital multimeter that you see over there. And this particular one I bought for about $20 from MCM Electronics. It's a pretty good meter. Nothing fancy, it's fairly basic, but it's a nice economical meter. If you see in the service literature a reference to a vacuum tube voltmeter or a VTVM, you can usually use a modern digital multimeter like this in place of the VTVM. VTVMs generally had an input impedance of about 11 megs, and these generally have an input impedance around 10 or so meg, so they match. The thing you don't want to do is, if it says that it used, when you look at these instructions, you see, for example, that they used a 20,000 ohms per volt voltmeter, well, then you don't want to use the modern multimeter without at least working out what the adjustments might be to the voltage levels. In other words, a 20,000 ohms per volt meter, and let me pause this for a second and show you one of those. This is an example of a 20,000 ohms per volt multimeter. Now let me show you where it says that. Right up here on the meter, I hope it'll stay in focus, it says 20,000 ohms per volt. And what that means is, if you're like on a 10 volt scale, 20,000 ohms per volt means that this meter will have an input impedance of 20,000 times 10, or 200,000 ohms, 200 k ohms. That's a far cry from the 11 meg that a VTVM or the 10 meg that a digital meter like that is. And in some circuits, it will load enough that you'll wind up with an inaccurate voltage reading. So if the original was measured with a VTVM, then you're safe using one of these. If it was measured using a volt ohm meter, then you have to make an adjustment for the difference in the impedance, particularly in a high impedance circuit, because the meter that was used back in the day, like this is a little more modern one, but back in the day there were a lot of these kinds of meters. There also were meters that were 1,000 ohms per volt, and of course they loaded the circuit even more than this. So those are a few things that you need to watch out for when doing voltage readings. So I've wasted enough time. Let's move on and get some voltages read. I have tried to arrange the video so that you can see the meter is reading 282 volts. It's currently connected to the 5Y3 and it's connected to pin 2, which, let me get this other chart, it might show a little better, which, as you see on this chart, the 5Y3, pin 2, it should be 280 volts DC. Now, that should be at a line voltage of 117 volts. Most lines these days run a lot higher than that. Some of them run in the mid 120s and some in the high 120s. What I have here is called a kilowatt, and if you can afford one, they're very, very useful because the adjustments on a variac like that are not very accurate. In other words, the readings on top of the thing don't really read the actual voltage. But the nice thing about these kilowatts is they're not that expensive, and they're a nice way to give you not only a voltage reading, but also a current reading. In this case, we're drawing 0.73 amps. So about 75 or 80 watts of power. What I have hooked up here is I have the ground lead connected to the, sorry about that, I forgot to tighten the pan on the camera, is connected in the back to a ground terminal that's also used for grounding the receiver. And then I'm using a little clip to connect to the tube. And the tube is standing up on a little Pomona socket adapter. This is an octal socket adapter, and I've probably shown you some of these before. They come in different types to suit, for example, this is I think a 9-pin, this is a 7-pin, this is another octal, and so on. They're very useful because they allow you to test the voltages from the top side without having to have the chassis turned on its back and so on. I find them quite useful. Well, once again, you can find those on eBay. I don't think they still sell those in general. So I think if you go to a place like Fry's Electronics, you won't find those adapters, but they may still make them, but you certainly can find them on eBay. So I had 283, now it's down to 281. And of course that'll move around a little bit depending on the load. So as the set warms up, that figure will move around a little bit, but it should be fairly close to what you read here. Now, what is it that we're actually looking at? Let me get the schematic out and show you that. Here is the schematic, and we'll move in on it so you can see the pin numbers a little better. And you see that pin 2 is this top lead. The rectifier takes the AC, which is off of this center tapped secondary, and rectifies it. The 5Y3 does not have a separate cathode. The filament is the cathode. So you take your high voltage off of the filament. Now there's a slight difference between pin 2 and pin 8, which is the other filament, but it's only a volt or so, 5 volts of AC. There's some difference in the DC. But you'll notice that the DC comes off of here, goes through a pi filter consisting of these two electrolytics. And what we're testing is whether there's anything in the receiver that's pulling this voltage down from where it should be. Let's move over now and test pin 8 and see what it reads. I've moved the test lead over to pin 8. And as you see, pin 8 is also reading 281.7 volts or so. This tells me that the electrolytics in this receiver are not pulling excessive current out of the power supply. So I'm going to go with those for now. At some point I may replace them, but I like to, if I can, leave a receiver as much in its original condition as possible. I wasn't always a believer in this, but over the last couple of years, actually over the last 5 years, I've changed my view on this. About 5 years ago, I was doing a lot of restorations and I was doing a lot of capacitor replacements. And I decided to test and see whether it made a lot of difference. So I took a couple of receivers, and in one I replaced the capacitors, and in the other I only replaced the ones I needed to. And what I discovered is that the receivers worked essentially the same either way, unless they were pretty old receivers. Now sometimes receivers from the 30s or 20s, you pretty much have to replace the capacitors. But if they still read good on a capacitance meter and with low leakage, I used to think it was a good idea to replace them anyway because they probably would wear out soon. Well, every one of those receivers from 5 years ago that I left the capacitors in are still working today. So I have decided to change my philosophy a little bit. And understand, different people have different views of this. Now, true connoisseurs of vintage receivers would prefer you leave them alone and only replace what you absolutely have to. And even then, if you have to replace something, try to use a new old stock replacement rather than a modern replacement, because some people are just they grate their teeth when they see a modern replacement in a receiver. Now it depends, of course, on the receiver and the person, but nonetheless, I've decided to do that in this receiver. Well, my meter is beeping at me, which tells me I've been talking too long, so I'm going to move on and do some more voltage, but stop the video at this point. The video is getting a little bit long for my taste, so I'm going to break it into another part, so there'll be at least 3 parts to this video. But before I do move on, I didn't find any serious voltage issues so far. Haven't quite completed it, but I thought before I move on to the next part, I ought to tell you kind of what I was trying to accomplish and give you some idea of why you might want to check the voltages before you move forward to check the functions of the receiver and some other things that we'll talk about in a second. Let me use this amplifier, this IF amplifier, as an example. This is the second IF. If there is leakage between the windings of this transformer, or worse, a short, the plate voltage from the preceding stage, that is from the first IF amplifier, this plate voltage here, will leak through and will upset the bias of this stage. It'll cause the grid to be too positive, or at least not as negative as it should be. What that will do is will cause more current in this tube, and more current in this tube will pull down the plate voltage. So there are 2 ways, or 2 voltages, that are rather critical on these IF stages. One is the grid voltage, and the other is the plate voltage. Now, I talked earlier about the impedance and the problem with high impedance circuits and low impedance meters. If you try to measure the grid voltage of a tube with a low impedance meter, a lot of times it will pull the voltage down. And the reason is, if you look at this circuit, you'll see that there's a low impedance path through the transformer, but then you come to a 100K resistor here. So if I used an example earlier of a 20,000 ohm per volt on a 10 volt scale. So if you try to measure that voltage, you're basically putting a 200K resistor in parallel with a 100K resistor, and that's going to substantially change the grid voltage. Measuring the plate voltage is usually a little easier because those are usually much lower impedance circuits, so the meters don't load them down. But that's what I'm doing, and the same thing is true when you get into the audio stages. Let's look at this AF amp. In this case, what you have to worry about is if there are shorts. For example, this capacitor is designed to keep DC off of this volume control. This capacitor is designed to isolate the grid from any DC that might be present there. If those two capacitors are leaky, then the bias of this stage will be upset, and so on. So, good idea to measure the plate and grid voltage there. Finally, in a stage like this, an output stage, it's a good idea to measure the cathode voltage, because that gives you an idea of how much current is flowing through this tube. And the output stage is an area in which you should be a little concerned about current. If it's drawing too much current, not only will it load down the receiver, but it also will shorten the life of the output tube and may shorten the life of the output transformer. So that's why I've been doing the voltage measurements before I start trying to do functions. The next step is I'm going to move over and start testing the functions of this. But since this video has gotten a little bit longer than I had thought, I think I'm going to wrap it up for now and beg your patience for a part 3, which will come hopefully in the very near future.